Welcome to Deep Learning Connects Weekend podcast series. Every weekend, we will bring a new AI research topic to discuss.
Today, we're diving into a fascinating paper called Defeating Nondeterminism in LLM Inference by Thinking Machines Lab.
Before we jump into the technical details, let's give our listeners a quick overview. What exactly is an LLM?
Great question. LLM stands for Large Language Model. Think of it as a computer program that can understand and generate human like text. Examples include ChatGPT, Claude, and other AI assistants that can answer questions and write content.
And what does deterministic mean in this context?
Deterministic means predictable. If you give the same input to a deterministic system, you should always get the exact same output. It's like a calculator answers if you type 2 plus 2, you always get 4.
So, the problem this research addresses is that AI models sometimes give different answers even when you ask them the exact same question.
Exactly! And that's a big problem for companies using AI in production. Imagine if your AI customer service bot gave different answers to the same question depending on how busy the server was.
That would be really confusing for customers. So let's break down what causes this inconsistency. Most people think it's about something called temperature settings, right?
Yes, temperature is the setting that controls how creative or random an AI model is. When temperature is set to 0, the AI should always pick the most likely next word. It should be completely predictable.
But even with temperature at zero, these models still give different results.
That's right! The researchers tested major AI services like ChatGPT, VLLM, and SGLang. Even at temperature 0, they got different outputs for identical inputs.
So, what did people originally think was causing this randomness?
The main theory was something called concurrency plus floating point arithmetic. Let me break that down. Concurrency means doing multiple calculations at the same time. Floating point arithmetic is how computers handle decimal numbers.
And why would that cause problems?
Well, when you add decimal numbers on a computer, the order matters. For example, if you calculate a plus b plus c, you might get a slightly different result than b plus c plus a. This is because computers can't store infinite decimal places.
So, people thought that because AI models run on graphics cards that do thousands of calculations simultaneously, the random order these calculations finish was causing the inconsistent results.
Exactly. The paper even shows an example where summing the same list of numbers in different orders gave 102 different results. It seems like a reasonable explanation.
But the researchers found this wasn't actually the main problem.
Right. Here's the key insight. If floating point order was the issue, then running the same matrix multiplication over and over should give different results. But when they tested this, they got identical results every single time.
So, the core AI calculations are actually consistent.
Yes, what they call the forward passedness, the basic computation an AI model does, NUNT, is actually run to run deterministic. Give it the same input, get the same output.
Then, what's really causing the inconsistency?
The real culprit is something called batch invariance. This is where it gets really interesting. Let me explain what a batch is first.
Please do, because I think this will be new for many listeners.
Think of a batch like a group order at a restaurant. Instead of processing one customer's order at a time, the kitchen processes multiple orders together for efficiency. AI servers do the same thing, NUNT. They group multiple requests together.
And batch invariance means the results should be the same regardless of batch size.
Exactly! Whether your request is processed alone or with 99 other requests, you should get the same answer. But most AI systems don't have this property.
Can you give us a concrete example of how this affects real users?
Sure, imagine you send a request to an AI server. If the server is quiet and only processing your request, it uses a batch size of 1. But if the server is busy and groups your request with 99 others, that's a batch size of 100. Even though your question is identical, you might get different answers.
So the server load essentially determines what answer you get.
That seems really problematic. It is. From the server's perspective, everything is deterministic NUNT. The same batch of requests always gives the same results. But from your perspective as a user, Other users are random, making your results unpredictable.
This explains why people have noticed AI chatbots seeming inconsistent during peak usage times. What's the solution the researchers propose?
They developed something called batch-invariant kernels. A kernel in this context is a small piece of code that performs specific calculations on the graphics card.
And these special kernels ensure consistent results regardless of batch size.
Exactly. The key insight is that you need to fix the order of mathematical operations regardless of how many requests you're processing together.
What specific operations did they need to fix?
Three main ones. First is RMS norm, which is a way of normalizing data. Second is matrix multiplication, which is fundamental to how AI models work. Third is the attention mechanism, which helps models focus on relevant parts of the input.
Let's start with RMS norm since you mentioned it's the easiest to fix.
RMS norm stands for root mean square normalization. Think of it as a way to standardize numbers so they're all on a similar scale. The fix uses what they call a data parallel strategy.
What does data parallel mean?
It means each item in your batch gets its own dedicated processor core. This way, the order of operations stays consistent regardless of batch size.
And what happens when you have more processor cores than items in your batch?
That's where it gets tricky. Normally, optimized code would use all available cores by splitting the work differently, but that changes the operation order and breaks batch invariance. So sometimes you have to accept lower performance to maintain consistency.
That sounds like a trade off. How significant is the performance impact?
For matrix multiplication, they only lost about 20% performance compared to the highly optimized scope VRESF library. For a complete AI server running the Qwen 3 8B model, their first version took 55 seconds versus 26 seconds for the standard version.
That's more than double the time. Did they improve it?
Yes, with better attention kernels, they got it down to 42 seconds. So the final version is about 60% slower, which is much more reasonable for getting guaranteed consistent results.
You mentioned attention was the most challenging to fix. Can you explain why?
Attention is complex because it involves multiple matrix multiplications plus various optimizations for handling long conversations. There are techniques like chunked prefill and KV caching that make things efficient, but can break batch invariance.
Can you explain KV caching for our listeners?
KV stands for key value. When an AI model processes a conversation, it needs to remember what was said earlier. Instead of reprocessing everything from scratch each time, it caches or stores the important information from previous parts of the conversation.
And this caching can cause inconsistency problems?
Right. Imagine you're processing the 1000th word in a conversation. In pre-fill mode, there are 0 words in the cache because you're starting fresh. In decoding mode, there are 999 words already cached. If you handle these situations differently, you get different results for the same computation.
So the solution is to make the processing identical regardless of what's in the cache?
Exactly. They update the cache first so the data layout is always consistent. But there's still the challenge of split KV for very long conversations.
What's split KV?
When you're generating just one word at a time during a conversation, there's not much work for all your processor cores. So normally you'd split the cached conversation across multiple cores to keep them busy. But typical implementations choose the split size based on available cores.
And that breaks batch invariance again because different batch sizes would use different split sizes?
Exactly. Their solution is fixed split size instead of fixed number of splits. Regardless of how many conversations you're processing, each split is always the same size, keeping the operation order identical.
This all sounds very technical to implement. Did they actually build a working system?
They did. They built it on top of VLLM using something called Flex Attention and Torch Library. The clever part is they can substitute their batch invariant operations without changing the rest of the code.
So existing AI applications could potentially just swap in these new components?
That's the idea. It's designed to be a drop in replacement for the standard operations.
Did they test this thoroughly? How do we know it actually works?
They did a really convincing experiment. They ran the same prompt, tell me about Richard Feynman 1000 times at temperature zero, using a large model.
And with standard inference, they got different results?
Yes, they got 80 completely different responses, even though temperature was zero and it should have been deterministic. The responses were identical for the first 102 words, but then diverged.
What kind of differences did they see?
For example, 992 responses said Feynman was born in Queens, New York, while 8 said New York City. These are factually equivalent, but textually different.
And with their batch invariant system?
All 1000 responses were identical, perfect determinism achieved.
That's impressive. But this has implications beyond just getting consistent answers, right?
Absolutely. One huge application is in reinforcement learning from human feedback, or RLHF. This is how AI models are trained to be helpful and harmless.
Can you explain how inconsistent inference affects AI training?
In reinforcement learning, you're supposed to learn from samples generated by your current AI model. But if your sampling during training gives different results than your inference during actual use, you're actually learning from a slightly different model.
So it's like practicing for a test with different rules than the actual exam?
Great analogy. The paper shows that this mismatch can cause training to fail partway through. With deterministic inference, you get true on policy learning with zero divergence between training and deployment.
This seems like it would make AI training much more reliable and predictable.
Exactly. And it challenges the AI community's tendency to just accept randomness as inevitable. Instead of just increasing error tolerances in tests or assuming systems can handle extra randomness, we should understand and fix the root causes.
Are there any other interesting technical details worth mentioning?
One important point is that this affects all types of hardware pairs, CPUs, GPUs, and TPUs all have this batch invariance issue. It's not specific to graphics card parallelism.
And they mentioned that newer hardware has some improvements?
Yes, they note that NV link sharp reductions are actually deterministic on newer hardware, but the batch invariance problem still exists in the software layer.
For our listeners who want to try this out, is the code available?
Yes, they've released the batch invariant operations library on GitHub at thinking-machines-lab/batch invariant-ops. They also provide examples showing how to run VLLM in deterministic mode.
Do you think this will become the standard for production AI systems?
I think it should. Once you understand that server load affects your results, it becomes clear that any serious production system needs batch invariance. The performance cost isn't that high, and the benefits for reproducibility and reliability are enormous.
Especially for applications where consistency is critical, like medical diagnosis or financial advice.
Absolutely. This research really demonstrates the value of digging deeper into apparent randomness instead of just accepting it. Often, what looks random has systematic causes with clear solutions.
That's a great lesson for researchers in general. Thank you for breaking down this complex topic in an accessible way.
Thanks. This paper is definitely worth reading in full if you're working with large language models. It's a perfect example of how rigorous engineering can solve problems that seem inherent to the technology.
For our listeners, we'll put a link to the paper in our show notes. Next week, we'll be discussing another exciting AI research paper, so make sure to subscribe.
Thanks for listening to Deep Learning Connect's weekend podcast series. Until next time, keep exploring the frontiers of AI research.
See you next week.